Welcome back to ECE 442-542. This is the review session for exam number 3. Displayed on the screen are the words behind the process for exam number 3, and the main piece is that we need, or that you can use 3 sheets of notes, plus you can have the transform table that you're comfortable using for the exam. Everything else is pretty much the same, although you might notice that this time I'm allowing you to bring in a compass. Just don't hurt yourself with that sharp point. If you're trying to sketch circles for a root locus, you might use a compass, but your drawings don't have to be that accurate. But at least you have an idea as to why I might be saying you could use a compass for this exam. In terms of topics for exam number 3, it's going to be the material for homeworks 5 and 6. And that's dealing now with these ideas. We dealt with transient performance and Z-plane pole locations, and you should be able to go back and forth between those. If I give you dominant poles, you should be able to translate that into settling time, percent overshoot, and peak time specs. If I give you transient performance specifications, you should be able to identify regions in the complex Z-plane that allow those closed loop poles or those dominant poles to satisfy those performance specifications. And in some cases, the performance specifications, you might have to tighten one or more of those in order to make all 3 simultaneously solved or satisfied. You also need to be comfortable doing the direct design method of Ragazzini, and based on previous lecture material, we should be comfortable designing P and PI controllers. And that's really the PI controller is putting down a 0 and adjusting the gain K to sketch your root locus. So sketching root loci with rules 1, 2, and 3 are what you'll be responsible for on exam number 3, and knowing those properties. So we'll get into the Ragazzini design, but the question concerned, I think, constraint number 4 of the Ragazzini design, which talks about steady state accuracy. And you may want to force your closed loop transfer function, your desired closed loop transfer function, to have a particular value or DC magnitude. You may want to force that T sub C of Z to equal 1, let's say at Z equal to 1. And that may require that you introduce a little bit more design freedom into T sub C of Z, which might mean putting in another 0 factor beyond what you might require by retaining unstable 0 factors and potentially allowing the zeros of 1 minus T sub C of Z to be located at the poles, the unstable poles of your original system. But we'll get to that when we get into the Ragazzini design. Here, if I give you a transient response, you should be able to do essentially a system identification. From this transient behavior, you should be able to calculate the settling time. Obviously, that's going to be subjective, but you're looking at when do I get within 1% of my final value. And that is where I would maybe then label that as my settling time. In this case, I've said, oh, suppose that T settles at 1 unit of time or 1 second. I'm now within 1% of that dashed line. My peak time, I can physically identify that on this response. In this case, let's say that occurs at 1/4. I can also calculate the percent overshoot. The percent overshoot is just the peak value of Y, which is right here. So now you would have Y max. And your percent overshoot by inspection of this diagram would be y max minus y steady state, where this line here is y steady state over y steady state times 100%. And once you now have that percent overshoot, you can now use the percent overshoot, the peak time, but you may want to just concentrate on the peak time and the settling time. That will give you a theta sub d and an r, and once you have an r and a theta sub d, you can find the dominant poles of a second order system. In this particular case, once we've looked at this particular plot, we can now find Z delta. What's the DC gain in this particular case? Or if I'm now trying to find suppose that this particular response, I'm told that a unit step applied to this system produces that trajectory. Then the DC gain times a unit step produces what numerical value for this picture that I've sketched? 3. And this unit step is 1, so now I know my DC gain of my system. I now know my DC gain of this G of Z is equal to 3. Or I now can say that from this, whatever I find for G of Z, whatever I've parameterized G of Z, if I evaluate that at Z equal to 1, I'm going to have to make that equal 3. So hopefully there's a parameter in my G of Z formula that will allow me to solve for that parameter to obtain a value of 3. But this may be the last step in my G of Z determination. How do I find my R and my theta sub D? That's what I want for Z delta. I'm now looking at an R e to the j theta sub D. What can I use in this particular picture to identify R or theta sub D? And now you have to just remember how to translate performance specs into closed loop pole locations or parameters in a closed loop pole. If I say settling time, what do you see? Circles or R. If I say peak time, what do you see? Now you see angles or theta sub Ds. If I said percent overshoot, now you're seeing logarithmic spirals or hearts. But we only need a theta sub D and an R, and we can find that from the peak time and the settling time. So in this case, if we looked at the peak time, which I said, oh, let's just by our eyeball say that the peak time is 1/4, the peak time is also pi over omega sub D. That was true for the analog case and the digital case. But in our particular world, in the discrete time setting, we're not so much interested in omega sub D as we are with the angle, theta sub D. And theta sub D is equal to omega sub dt. So that now, theta sub D, or I'm sorry, we could solve omega sub D for theta sub D and T and we now could solve this for theta sub D. We now know that theta sub D is equal to pi t over 1/4. And somebody might have to tell us what capital T is in this case. And we could now plug in capital T and scale that by pi, again, this theta sub d is in radians. And now we have our angle. We could find our radial distance from our settling time, and there, whether that's given to us in terms of sample periods or absolute time, in this case, I think I said, oh, let's let it be 1. Somebody would have to tell us what capital T is in order to now solve for R. What do we know? Well, or, yeah, they would. So in this case, our expression, if somebody gives us capital T, we could solve for n sub s. Once we know n sub s, we can now solve for R. And once we have R, if somebody says, oh, suppose that your g of z had a 0 at the origin. Maybe somebody tells you that. Or they tell you you have a pole 0 excess of 1 in your second order transfer function. Then we now know that we have alpha z, if we had a 0 at the origin, and we have z minus r e to the j theta sub d, and we have z minus r e to the minus j theta sub d. And how would we find alpha? That's where this DC gain formula comes in. We know R, we know theta sub D, we know everything in the denominator. We can now replace Z with 1, set that equal to 3, and solve for alpha. And now we have identified that system that gave rise to that transient response. And you'll need to be able to do that on the exam. Start with a transient response and create a transfer function, a second order transfer function, g of z. Another way of creating a transfer function is by you being given particular design specifications. And here, when I was looking at this, what do you think about when I say percent overshoot? What shapes do you think about? This is now our zeta, or this is now our hearts. So those are now red. What about peak time? This is now angles or theta sub d, or wedges, and our settling time. Those are the R or the circles. And so if somebody gives you this breakfast cereal mix of performance specs, now when I was looking at that, red hearts, green angles, and R circles, I thought of Lucky Charms. They're magically delicious because of their slogan, which I had to look up when I was thinking of this, and that's pink hearts, yellow moons, orange stars, and green clovers. Well, we don't have those shapes, but we do have red hearts, green angles, and black circles. So yes, I had to look that up. I was singing that limerick or that tune, and well, here I guess I have blue circles, so I've changed my color scheme. I wouldn't make a very good advertising executive. But here's how you now would want to fit those into desirable locations for your closed loop poles. Given a wedge, which is an angle, theta sub d, that's the peak time. Given a settling time spec, which are the circles, and given percent overshoot, which are these logarithmic spirals or hearts. And what's a default way to be thinking of this? A lot of times, reducing the radius is the one that makes you meet most of these specifications more easily or more effectively. If you shrink your radius along the same logarithmic spiral, you're going to be reducing your settling time and keeping your percent overshoot the same, and also speeding up your peak time. As you now move along this particular curve, you're fixed on your percent overshoot, but your radius, your distance away from the origin, is shrinking, and your angle is increasing, which gives you a quicker peak time. But make sure that you read the question carefully, because I actually might want you to identify a region that has a percent overshoot of this much or more. Then you're saying, oh, I need a zeta value that's this value or less. Or I might say, what about a settling time of this amount or larger instead of this amount or less? Because I may want to push you around in the z-plane to give me regions of acceptability to meet particular performance specifications. So just make sure that you're reading carefully whether I'm saying less than or equal to or greater than. But all of those are then connected to this next possibility, is can you determine percent overshoot, settling time, and peak time given z delta? So if I now say, oh, here's a k value, you should be able to find your closed loop poles. Once you have your closed loop poles, can you from those locations extract a percent overshoot, peak time, and settling time? And here, if you're trying to find the notes for that or the table, I believe we derived those on the 22nd of March. That table of these different relationships between R, theta D, and zeta. Which, if you now if somebody gives you z delta, which is r e to the j theta sub d, what does r translate into in terms of performance? The circles give you your settling time, which are now influenced by this relationship. Theta sub d, what performance spec does that correspond to? That's our angle. That's our peak time, so that now time to peak is pi over omega sub d, but that's pi over theta sub d over t, or that's pi t over theta sub d. So if you know theta sub d, you can calculate your peak time. And if somebody now gives you an r and a theta, we didn't derive this, but you should be able to derive this. You can actually find your zeta value in terms of r and theta sub d. That's now the natural log of r over theta sub d squared plus the natural log squared of r, all square rooted. And it has a similar structure to what you're used to seeing with percent overshoot and pi. But now, if I give you r and theta sub d, you can actually find the percent overshoot for that choice of r and theta sub d, where the percent overshoot is now 100 e to the minus zeta pi over the square root of 1 minus zeta squared. So once you have this zeta, you can plug it in there to obtain your percent overshoot. And that's how you would now start with a dominant pole pair, z sub delta, and produce these performance specs. Yes? It's e to that whole thing. So that exponent is minus zeta pi, all divided by the square root of 1 minus zeta squared. That's the exponent of e. So here's our Ragazzini design. With the Ragazzini design, we're trying to find an acceptable closed-loop transfer function, T sub c of z. And on the exam, I'm probably not going to have you find the resulting controller. The hard part is producing T sub c of z. The other is basically algebra, to plug it into the design formula. But the whole point is R1, restriction 1, you're trying to make sure that your control law is causal. And what's causality? Well, we need to preserve the same pole zero excess in T sub c that we had in our plant, or at least have that much pole zero excess or more in T sub c as we have in our plant. Restriction 2 concerns unstable zeros, which means that we want T sub c of z to have the same unstable zero factors that our original system had. So we're trying to build T sub c of z. For what reasons? Why do we have these two restrictions when we apply this design approach of Ragazzini? With these restrictions 2 and restrictions 3, what we're trying to do is make sure that our resulting controller is not canceling poles and zeros outside the unit circle. That's the whole point of restrictions 2 and 3. We're trying to make sure that our resulting controller does not try to cancel poles and zeros that live outside the unit circle. So we're forcing those cancellations to really happen inside T sub c of z. So this makes sure our resulting controller C of z does not cancel poles and zeros outside the unit circle. And we're actually selecting or designing T sub c of z to ensure this happens, that we don't have C of z canceling poles and zeros outside the unit circle. If we wanted to, then we could, once we've designed, and the steady state accuracy spec is potentially this guy. You may want to force the DC gain of your desired closed loop transfer function, T sub c of z, to have a value, a magnitude of 1 when evaluated at z equal to 1. If you want even more, if you want certain steady state error due to a ramp input, then you have to worry about the velocity gain constant, which I think we've included in earlier notes, but just sort of in passing. That's requiring a few more steps in the process, but that's what restriction 4 is concerned with, is the steady state accuracy. Let's look at an example. Suppose we start with G of z having a real zero at 1/2, a pole at the origin, and another pole at 1. And maybe our goal of our closed loop system is to have a deadbeat response. Is it clear what I mean by a deadbeat response? If I say deadbeat response, I want all of my closed loop poles to be located where? At the origin. So I now know what the poles of T sub C of Z, where they are located. They're all going to be at the origin if I say a deadbeat response. If I say I want them to have the dominant behavior satisfying these performance specs, then you have to go up in what we talked about before and use those performance specifications to determine a given pair of poles Z sub delta. In this particular case, can we use T sub C of Z equal to 1 over Z? Does that make sense? Or does that seem reasonable? Or what's another possibility? Maybe we want to say K over Z. Maybe we want to say, oh, let's at least give us one parameter. Is this closed loop transfer function deadbeat? Yes, it has a pole at the origin. Does it meet the restrictions that we might, or the constraints? Restriction 1. What's restriction 1 say? That's the causality constraint. What is the causality constraint? What's our pole zero excess in our original plant? 2 poles, 1 0, a pole zero excess of 1. What's the pole zero excess of T sub C of Z? 1. So that meets our causality constraint. If we need more parameters for flexibility, then we would need to put in another zero factor, but we can't just do that by itself. We would have to maintain the causality constraint, so we would have to bump up the number of poles by 1 if we put in a zero factor. And we might just keep inputting or increasing those zero factors if we need more and more freedom in our design. So R1 would be true if we keep this strategy of keeping our pole zero excess of 1. What about restriction number 2? Yes. The question was, if we had a pole at the origin and then we had 2 poles with imaginary components, and I'm assuming they're inside the unit circle, now they're no longer going to be deadbeat, because now they're going to oscillate, or they're going to, what, collapse, theoretically, in an infinite amount of time, not in a fixed number of steps. The deadbeat response says, oh, if you have 2 poles at the origin, then after 2 sample periods, you've beat your response down to where it's locked on to its final value. But if you have now a radius for your closed loop poles, that radius will collapse if it's less than 1, but it's going to take more than a finite number of steps, in theory, to shrink to 0. So it's no longer a deadbeat response. Yes? So the question concerned requirement 3. Requirement 3 says we want to make sure that our 1 minus T sub C of Z has a 0 at the poles of our plant that are outside the unit circle. I should say on or outside the unit circle. We really don't want poles in our system to be canceled on the unit circle. So now we want to not cancel that pole at Z minus 1. And to make sure that's the case, then we would have to invoke Rule 3, and Rule 3 then is dealing with 1 minus T sub C of Z, evaluated where? Well, at the pole that we're trying not to cancel with our controller. And that pole, in this case, is at Z equal to 1. So we don't want our controller to cancel that pole at z equal 1. So any poles on the unit circle in our plant, we would want to impose restriction 3. In this case, it's real, but it could be complex, and then we would have to make sure that we made those satisfy this 1 minus t sub c of z, and that's a reason why we might have to introduce more flexibility in our zero factor or zero polynomials of t sub c of z. Do we need to worry about restriction 2 in this example? Restriction 2 was actually concerned with zeros outside the unit circle. In this case, the 0 is inside the unit circle, so we're okay. We don't have to worry about restriction 2. What about restriction 4? We didn't say anything about steady state accuracy or sinusoidal response behavior. I'm sorry, steady state accuracy behavior. So this one, we don't need to worry so much about. Question?
Yeah, so like so far we've only seen poles that are like so outside the unit circle. Like for R3, we see where there'd be like one pole outside the unit circle, but that one would be multiple poles outside the unit circle.
So now if there are multiple poles outside the unit circle, we might have to start putting more factors in here to give us more parameters, alphas and betas, so that 1 minus t sub c of z gives us the flexibility to make that equal 0 at those given pole locations.
So we would still evaluate it as poles.
We would,
We evaluate it as poles.
yes, so now let's change this. Let's say that this is, let's say this is z minus 4. Then one of these we would have to evaluate at z equal to 4. We would also have another one where we would have to say 1 minus t sub c of z at z equal 1 needs to 0. If we had both pole factors z minus 1 and a pole factor z minus 4. And that would give us our alpha and beta, potentially. In our case, if we looked at k over z for this original piece, now I'm sort of back to this situation. Now that would equal 0 as long as k was equal to 1. And that would force k to be a specific number in that unknown k over z desired characteristic or desired closed loop transfer function t sub c of z. This is no longer in play. This one would be at z equal to 1, and so let's just forget that comment, and now we need to pick k to make this equal to 0, and that's going to be true as if we let k equal to 1. This is assuming now that t sub c of z was that k over z, and we're evaluating it at z equal to 1. But now you can actually answer this additional question relative to steady state accuracy. For this particular plant, we actually had an open loop pole at z equal to 1. Our g of z was this. What's that pole, open loop pole at z equal to 1 do for us in terms of steady state accuracy? or error due to a constant input. Now that's like the integrator in our PI controller. It's just that that integrator is in our plant that we started with, which this will actually give us 0 error to a constant input. If we keep going with this example, if we plugged in that T sub C that we just calculated, which was 1 over Z, into this design formula for our controller, T sub C is 1 over Z over 1 minus T sub C, getting a common denominator, in both the numerator and denominator, we end up with that ratio T sub C over 1 minus T sub C being 1 over Z minus 1. We can plug that into our C of Z formula, and now you can see that by our choice of T sub C of Z, we aren't allowing that Z minus 1 factor into C of Z to be a 0 factor to try to cancel that pole in our open loop system. So we're avoiding that by the choice of T sub C of Z. So it's canceling in this expression or design equation for C of Z so that we don't have that factor as a 0 factor in our C of Z expression, which it would pop up into the numerator if that Z minus 1 factor wasn't in the denominator of our T sub C over 1 minus T sub C expression. And now we have a controller that's Z over Z minus 1/2. And what does that do for us? Here is our C of Z. Here was our G of Z. And you can see then that this Ragazzini design is actually canceling stable poles and zeros by design. It's trying to invert that G of Z, but we force it not to cancel poles and zeros outside the unit circle. That's restrictions 2 and 3. But now we end up with the Z's canceling and the Z minus 1/2 canceling such that we now have, if we make all of those cancellations, this simplified block diagram. And we can use our cheer, G over 1 plus G, to compute the closed loop transfer function, and it ends up being, now we found the answer in the back of the book, and it agrees with what we designed it to be. We said we want T sub C of Z to be 1 over Z. Oh, by that choice of controller, C of Z, we've now achieved what we set out to do. And if we move back to earlier in the semester and somebody says, well, okay, you've designed a controller. Now maybe they say, can you build that in a computer? Can you realize this controller transfer function? We know what C of Z is. C of Z, we just computed to be Z over Z minus 1/2. And we can now find the difference equation relating the air signal in our block diagram to the input waveform U that drives our plant. We can do that by rewriting this in terms of delay elements by scaling the numerator and denominator by the highest power in the denominator, which is Z to the minus 1. So that now C of Z, written in terms of operator Z to the minus 1, is 1 over 1 minus 1/2 Z to the minus 1. Cross multiplying, we end up with the input U of N equaling 1/2 U of N minus 1 plus E of N. So that now you measure the air signal at the present time. I use that to create the input to the plant by remembering what the input was one sample period before, scaling that by 1/2 and adding that to my present air. And this is now the difference equation you would implement in your computer to accomplish this desired closed loop transfer function for that particular system that we started with. And the controller is not that complicated. It's a first order controller. Let's finish up by exercising our root locus construction capabilities. Let's walk through some basic root locus patterns. Can you now sketch the root locus of this pole zero pattern on the left? And some of these are very challenging, I admit. What's the root locus for this pole zero pattern on the left? If you look at any point here to the left of that pole, they are going to see an odd number of poles and zeros. And as I crank up the gain K, I can move my closed loop poles from some pole that's to the right of 1 and move it all the way to minus infinity. Is it possible to stabilize this closed loop system for some range of K? If I ask that, now you're thinking about this and you're saying, oh, does K equal 0 stabilize that system? No, I have to crank up the gain to at least get me to this minimum value of K, which is now the K expression, the K formula, evaluated at z equal to 1. And the maximum that I can crank up K and still remain stable is this squared value. This is now K max, which is now the K formula with z evaluated, or with the K expression being evaluated at z equal to minus 1. That's now your K range for stability. What about the pole zero pattern's root locus on the right? How many real axis line segments exist? 3. We've chopped up our bread into 3 pieces. Are any of those real line segments on the root locus? And is there one? And which of those is it? Is it to the right of the pole? Is it between the pole and the 0? So here is our root locus. Now as I increase K from 0 to infinity, do I have any hope of stabilizing that system? All hope. Any value, any non-negative value of K will stabilize this system. Every possible choice of K between 0 and infinity will keep the closed loop pole. How many closed loop poles do I have? 1. So here, if I said, what's the range of K for stability, you would say from 0 to infinity for K. All based on a quick sketch of the root locus for that pole 0 pattern. What about this pattern? How many real line segments exist? Again, there's 3. How many are on the root locus? 1, and which one? The one between the pole and the 0. Now as I crank up the gain K, I move from that pole to the 0. Are there any values of K that might make this system stable? Question? So now the maximum K is when I get to that 0. And that will be k equal to infinity. But is that a stable location? It depends on the size of my unit circle relative to the, if my unit circle is there, do you see that I now have a limited range of k for stability? Now my minimum gain is found at what value of z? Now I would evaluate my k expression at z equal to -1. That's the minimum k. The maximum k would be at evaluating z, the k expression at z equal to 1. Is that clear? What about the next pole zero pattern? How many real axis segments exist here? 3. Are any of the real axis segments belonging to the root locus? How many branches of the root locus are on the real axis? 2. How many closed loop poles do I have? 2. I have 2 branches on that one real line segment that lives on or is a part of the root locus. Now I only have 2 poles. This guy goes right, this guy goes left. What happens now? They meet in the middle and they go off at plus and minus 90 degrees. And in this case, halfway between, they're separated by 0.6. So halfway is 0.3. 0.3 to the right of 0.2 is now at 0.5. So if I now sketch this, that's now my root locus. Do I have any hope of stabilizing my system for a choice of k, non-negative values of k? What's the minimum value for stability? 0, because they're both starting inside the unit circle. Now I have a unit circle that's there. Can I continue to crank up the gain k to an unlimited value? No. Can you find the gain to get me to that upper limit? You know quite a bit already because of this special structure of the root locus. You know that this z upper limit, let's say z triangle, has a real part of 1/2 because that's right where that root locus is living. Is it a real part of 1/2? What we may not know is that y location. What if I call it y bar? But can you find y bar? What do you know about that triangle? It's on the unit circle. How far is the unit circle from the origin? 1. So we know the magnitude of that complex number, z delta, has a magnitude of 1. So in this case, we now could say, oh, I know that 1/2 plus jy bar must equal 1, the magnitude of that complex number. Or I now know that 1/2 squared plus y bar squared is equal to 1. Or I now know that y bar is equal to the square root of 1 minus 1/4. Or y bar is now a square root of 3 over 2. Or this 0.866. So now I know what y bar is. Does that help me in any way? Now I can actually find the k value. What's the k value? Well, I know k for that pattern of pole and zeros, the magnitude of kg has to equal 1. I solve that for k, and I now have this formula, z minus 0.2, z minus 0.8. And if I want to know what's the upper limit for stability, I now want to know what's k delta. Or now I'm evaluating this at 1/2 plus j square root of 3 over 2. And you can plug in a complex number for z. All you're doing is finding the magnitude of a complex number. And in this case, they are equally away from that root locus, so one should have exactly the same magnitude of the other. If you find one, you can square it, and that will give you your gain k to get you to that maximum location for k of stability. What about this pattern? We've talked about this today. I've talked about it in an earlier lecture for homework help. It's this special pattern of poles and zeros. We have two real poles to the right of one real zero. And now, what do we know about the root locus? How many real axis segments do we have? 4. And how many of those 4 are on the root locus? Any of them? So we have this and we have this. And if we just had to quickly sketch this, we would say, oh, this is a circle. The center of that circle is at the 0 location, and the radius, in this case, this radius is the geometric mean of the distance between the 0 and the first pole and the 0 and the second pole. If I put some numbers to this, what if this happened to be 1/2 and this is 1 or 2 over 2, and let me call this Z1. This is the same radius. And what is R? R is the geometric mean of the different distance, or the geometric mean of the distance of Z1 to P1 and Z1 to P2. Where L1 is now, let's say, 1/2 minus Z1, and L2 is P2 minus Z1. That radius then could be added to that 0 location to give us the location between those two poles where we break away. Now you could use the formula for k. In this case, k times the 0 factors and the pole factors all have to have a magnitude of 1. This would now be z minus 1/2 z minus 1 all over z minus z sub 1. And if there was a constant in our transfer function, that would be an alpha, which would be downstairs. We can now plug in different values of z between 1/2 and 1 and find where is the relative maximum. You could numerically do that with your calculator if you wanted to. You could plug in numerical values for z. Of course, you would have to know what z1 is, but you could now find the numerical value for the relative maximum of k between 1/2 and 1, and it should be consistent with this geometric mean calculation that we just calculated. And you might see that formula on previous exams or old exams. And numerically, now you're just sort of saying, oh, it's probably somewhere close to 1/2 the distance between 1/2 and 1. Let me just numerically examine that and try to find, and on an exam, you're not looking for 5-digit accuracy. And depending on what you're asked for, you wouldn't even have to find that value. You could just say, I know it's between those. Let me just draw a circle. Now, what do you know about stability? It's sort of like that, maybe. based on the radius. Because the 0 is to the left of the origin, now what happens relative to, where's my minimum value? If this is the case with the unit circle relative to that root locus, what's the minimum value of k for stability? 0. What's the maximum value? Those are supposed to be complex conjugates. But my 0 and drawing are a little bit off. But you would now calculate to get you what? Until you exited the unit circle. You would need to find that triangle location. But you know that the magnitude of those is equal to 1. And you could use that to help you, and you could look at the closed loop polynomial as a function of k and use that also to try to find that location. What about the root locus for this pole 0 pattern? Are we okay with that sketch? It's pretty quick to start to find these root locus diagrams. Is this system stable for any choice of k? What do you need to check for stability? You could check that location, and you could check the gain formula at that location. If this system is, let's say that k triangle is 6, and let's say k squared is 5. Is this system stable? Will this system be stable if the gain to get me to -1 is 5 and the gain to get me to 1 is 6? Do I have any chance of stabilizing this system with a constant gain controller? Now as I crank up the gain from 0, I'm not stable at 0 because that pole is outside the unit circle. I crank it up to 5, and oh, that pole that's in the left half plane is now right on the stability boundary, and that pole that's to the right of 1 is not yet to the unit circle, because it's going to take a gain of 6 to get it inside the unit circle. But when I hit 6, that pole that's in the left half plane is now zipped outside the unit circle. So if you calculate the gain at those two locations in the z-plane and find this relationship between k delta and k square, you can say there's no range of k that will stabilize this system. What if it was different? What if k square was now 10 and k triangle was 4? Do you now have a stable range of k? It's all going to depend on the relative locations, excuse me, of these poles and zeros. In this case, you would have stability between 4 and 10. K living between 4 and 10 would allow you to stabilize that system. And it was a quick determination. You would just have to use the magnitude condition to find the k expression, evaluate it at 1 and -1, and then do this check. Do I have any range of k for stability? What about this pole zero pattern? We haven't gone there yet, have we? How many poles do we have? Can you find the real line segments that belong to the root locus? You can start stepping through these rules even though we haven't gone all the way, but now you know that segment is on the root locus, and you know this segment, that's supposed to stay on the root locus. How many zeros at infinity do you have? 3. You have a pole zero excess of 3. So in this case, you have 3 branches going off to infinity. And the main, or the fundamental angle is 180 divided by that pole zero excess. So you know that one asymptote is actually going off at an angle of 60 degrees. And we will talk about this, which I think is our rule number 4. We will have asymptotes they'll basically divide our 360 degrees into equal wedges or sections. In this case, we have our fundamental angle measured relative to the real line of 60 degrees. Well, we have another one going off at 180, so we know that these wedges are 120 degrees apart, or these asymptotes. We obviously are going to break away between 1/2 and 1, and this one's going to go here. Whoops, I wanted that to be red. This will go here, and that will go there. And we could, if somebody gave you that sketch, could you now determine, at least diagrammatically, values or locations that might help you determine stability? Is k equal to 0 stable? Yeah, you're on the margin, aren't you? You're right on the boundary. But now you would be looking at gains here and gain there. And checking to see if you have all 3 branches simultaneously in the unit circle for those locations of closed loop poles. What about this one? It should be really very easy to find the real line segments that belong to the root locus. You're just standing in a point and saying, is there an odd number of poles and zeros to my right? Doing that, I could see that there's a part of my root locus. Here's a part of my root locus. 1, 2, 3, 4. Here's a part. And those are now my segments of real axis segments that belong to the root locus. How many zeros at infinity do I have? 2. So now I have 180 divided by 2, and we know what that looks like. We know that that's now this 90-degree. Let me just draw it here to exaggerate the fact that it's probably not going to be halfway between those 2 poles, but now we will have this going off to a 0 at infinity, that one going off to a 0 at infinity, that one going to a finite 0, and that one going to a finite 0. And that's now the root locus. And depending on where those are at relative to the unit circle would determine whether or not that is a stable system or not. Question? So the asymptote, we'll talk about that after exam 3, but that will be related to the sum of the poles and the sum of the zeros and divided by the pole zero excess. We'll learn those strategies for the centroid of that asymptote after exam number 3. So that would tell us where those asymptotes are centered. They're centroid on the real line. And here's our classic, but now you should be good to go on this one. This is the special case, and I have a video and notes for this special case. This is 2 real poles to the right of 1 real zero. How do I find the breakaway? Very quickly. Geometric mean between the center, the Z1, and the 2 poles. So it'd be A minus Z1, that length, times B minus Z1, that length, square rooted. I now know my radius. And I use that radius with my compass. I put the tip of my compass on the 0, which is the center of my circle, and I now draw my circle of that radius, which in this case might look something like that. Whoops, they're supposed to re-enter at the same point. And whether or not this system is stable will obviously depend on the locations of A and B. If my unit circle was right here, can I stabilize that system with constant output feedback? Never, can I? The pole A always is outside the unit circle, and it never comes inside the unit circle. If my unit circle was somewhere else relative to A and B, if my unit circle now was this, gosh, that's a good unit circle, but now you do have a chance. Now they do break away inside the unit circle. You're going to have to crank it up a little bit beyond 0, but now you'll have some range of K that will stabilize that system. Questions on that? And what would you do? You could pick those, and now I might say pick closed loop poles to locate them at the squares. Now what's your settling time, percent overshoot, and peak time? You can get that from the squares. You find their radius away from the origin and their angle, and now you back out those performance specifications from that complex pole location. And it's all coming full circle. No pun intended. Good luck on exam number 3.